proposed this talk, I was at the beginning of my work in multimodal classification, and the research took an interesting turn, which I think you'll see in just a minute. I hope this is still very useful for you. Okay, so we're not just talking about multimodal classification, we're talking about outperforming. Oh, is it not loud enough? Is this better? Alright.
Technical issues.
Okay, just let me know if you need anything else. Are we good?
A little bit better.
A little better? Not enough better?
A little bit better.
Okay. Well, I'm going to continue. Okay, so we're talking about outperforming multimodal classification. Here's a broad outline of what we're going to be covering. So this work is centered on a particular task. We're going to be predicting human-applied movie genres. And we're going to be using data from the Multimodal Dataset, released in 2017 by Seale. Now, if you yourselves are interested in working with this dataset, it is available online, and it's easy to Google for it. You may be asking yourself, what is multimodal? Well, for this particular work, it's going to entail using two modalities. Mode 1 is text, and mode 2 is image. So let's take a look at an example from the dataset. Here we have a movie poster for the movie What the Bleep Do We Know? And then we have the beginning of the movie summary, and the human applied genres. So the humans think this movie is a documentary, a comedy, a drama, fantasy, mystery, and sci-fi. All of those things. You know, good luck to us to predict that. When we look at just some descriptive statistics on the data set, we can see that there are 27 genres, and we can see the number of movies applied, or that those genres are applied to. So we see everything from just one movie in the reality TV genre to 13,967 movies in the drama genre. We're going to go ahead and take out the genres in the lower 25th percentile, just so that we have good training and validation sets. So it leaves us with 20 genres. We still have a good number of genre-labeled movies. And on average, we're going to have around 3,000 movies per genre. But again, we still have a lot of imbalance in the classes. Drama has 13,967 movies. Western has 705 movies. On average, you're going to see about 2 human-labeled genres per movie. So What the Bleep Do We Know is a little over-labeled. And then we're going to see 164 words per movie summary on average. If we look again at the data set, you can kind of see where we're going to have okay, you can see my pointer, that's good. You can see where we're going to have an average of 2 genres per movie. Okay, let's look at the previous researchers who attempted this task. The first research team is Seale and al. National University of Columbia. They released the dataset, and they were the first ones to try to predict the genres using a multimodal model. Following suit is Seale et al. At Facebook. Both of the teams tried text-only models, image-only models, and various fusion methods like mixture of experts. Both of the teams find that a gated fusion is the best approach. So let's take a closer look at a gated multimodal fusion method. This is the fusion method used by Seale et al. In 2017. So you can see that all of these equations are differentiable, and they're meant to be one unit that is interoperable with all neural networks, and you can train them with stochastic gradient descent. So here you have x sub v. Now this is the output from an image classifier. V stands for vision. We weight that output and put it through a tan h function so that the output of this equation is anywhere from -1 to 1. We do the same thing with the output from a text classifier, x sub t. Then we concatenate the output from the image classifier and the text classifier, weight it, and put it through a sigmoid function. So the output is anywhere between 0 and 1. Now here you see the gating part of this fusion method. We're going to take anywhere from 0 to 1 and multiply it times anywhere from -1 to 1. Then we're going to subtract anywhere from 0 to 1 from 1 and multiply it times anywhere from -1 to 1. So you can see that at times we're going to get more or less of the output from our image classifier, and at times we're going to get more or less of our output from our text classifier. This is basically an attention unit, a gating, to help us to learn which attributes of these two modalities are the most important for our classification. Okay, so let's see how our teams did. Arevalo and al. They obtained a micro F1 of 63 using a gated multimodal unit fusion of an RNN with word-to-vec embeddings and a resnet. Seale et al. Got a micro 51 of 62.3 using a fusion of fastness and BGG. Here in the parentheses, you can see the micro F1 scores for each of these classifiers when they're used as standalone units. What's interesting about this information is that you can see that neither the RNN nor the ResNet achieved the 63, but when we fuse them together, we get more than the sum of our parts. So this is good. This kind of means that the text classifier is providing information that the image classifier isn't, and vice versa. When we fuse them, we get better classification. Okay, so some of you may be saying, well, what's a micro F1? Let's start with an F1. An F1 is an average or a harmonic mean of precision and recall. You get a micro F1 when you compute the F1 over all of the classes, so that classes with more observations have more weight, classes with less observations have less weight. Now, you can also compute a macro F1, where you compute the F1 independently for each class, and then you average it. Now this treats all the classes equally. If you have imbalance in your classes, you're going to want to use the micro F1 for a more accurate measurement. Okay, so that's the past work. Let's look at the recent work, which is stuff that I've been doing. My top score is an F beta of 73.4. This is a 15% improvement over the previous scores. What is an F beta? That's a micro F1 that weights recall slightly over precision, so it's a little strict. Okay, so how did I achieve that score? Well, I didn't use multimodal fusion. I just built a text classifier, but it's kind of involved. So we're going to spend the rest of this talk figuring out what went on. So first of all, we used a transfer learning method called ULM-FIT, which is Universal Language Model Fine-Tuning. That was first developed by Howard and Rudder in 2018. And we're going to use this transfer learning method on an AND-LSTM, first developed by Merity, and we're also going to use one-cycle learning, first developed by Leslie Smith. Okay, so let's talk about this Universal Language Model Fine-Tuning method. In this method, you take a pre-trained language model, you fine-tune it on a new data set, and then you create a text classifier out of the language model. What is a language model? We're going to use a word level, not a character level, but a word level language model, which is going to predict the next word in a sentence. Now, the word level language model that we're going to use as our pre-trained general domain word level language model is the Wikitext 103 model. Now, it is an AND-LSTM trained by Howard et al. Using one-cycle training, and it is available to you in the FastAI library. Here's a little bit more on the data that the Wikitext 103 model was trained on. It's trained on around 29,000 good and featured Wikipedia articles, and it has 103 million tokens, which makes it huge. Okay. So what is this AND-LSTM? It's a non-monotonically triggered average stochastic gradient descent weight drop LSTM. And hopefully this will become very clear to you soon as to what all of this is. Okay, so what is this non-monotonic trigger? Well, the non-monotonic trigger is going to be used to initiate an averaging of stochastic gradient descent when a validation perplexity metric fails to improve for multiple cycles. So it's tracking perplexity. Perplexity is how well the model predicts the next word. It's the percentage of words that it gets correct. When you feed it a text, it's going to say, oh yeah, the next word is, the next word is, the next word is. And so all the times it gets right out of all the times it could have gotten right, that's our perplexity. So it's the non-monotonic trigger is following this perplexity metric. And the cool thing about it is that the perplexity metric doesn't have to fail like this. It doesn't have to fail in a monotonic fashion. It can get a little bit better, and then get a little worse, and a little bit better, and a lot worse. And we're just tracking it over multiple cycles. So it's not a monotonic trigger, it's a non-monotonic trigger, and it allows for some variation in how the perplexity metric is performing. So what is this averaging of stochastic gradient descent, or average stochastic gradient descent? Well, basically, this non-monotonic trigger is going to be measuring the perplexity, and it's going to say, oh, the perplexity is not improving. It's been several cycles. I'll tell you about cycles in just a little bit. It's been several cycles, and so let's average the stochastic gradient descent rather than taking the last iteration solution. What does that do for us? It reduces noise in the model. It's a regularization technique. Okay, so we're doing this on a weight drop LSTM. There's kind of a problem with LSTMs when you're trying to randomly apply dropout, and that is when you randomly apply it to the hidden state, it interferes with the maintenance of learned relationships over longer sequences. So the solution to this problem is to define regions for dropout along the first matrix dimension of the input, the sequence dimension, using a mask. They call it the drop connect mask. You define, so in our input for this model, we're going to have 70 words of input. That is the first matrix dimension, the sequence dimension. So we've got a sequence of 70 words. We're going to apply this mask that says, hey, drop out the second word, drop out the 56th word, drop out the 67th word, and so on. And do it throughout the entirety of the LSTM. Do it along the hidden-to-hidden weights, which get multiplied into the hidden state of the LSTMs. So what this helps us to do is maintain learned relationships over longer sequences. Let's do a short model recap. We're going to be using a Wikitext 103 model, which is an AWD LSTM, and it uses advanced optimization and regularization techniques. So that's our pre-trained model. Let's go a little bit more into how it was actually trained. So Howard et al. In 2018 trained a Wikitext 103 model using slanted triangular cyclical learning rates and one cycle training. So let's just step back a little bit. Like slanted triangular learning rates and one cycle learning. What's cyclical learning in the first place? Cyclical learning is where you're going to set minimum and maximum learning rates. Those are set as hyperparameters, and you're going to cycle through them. A cycle has two steps. In the first step, you increase the learning rate while slightly decreasing the momentum. And in the second step, you decrease the learning rate while slightly increasing the momentum. The step size that you're going to use is the number of batches through which to iterate. And so that's just set as a hyperparameter. Slanted triangular cyclical learning is where you start at a low learning rate and you quickly follow linear descent to your optimally high learning rate, and then you follow a slow linear decay over the second step. Slanted triangle. Very simple, yes? I'm seeing looks of confusion. Hopefully we can cover some more of this in the question and answer period. Okay, so I said right here that in our first step, we're going to an optimally large learning rate. Well, there is a callback which is going to be triggered. So when we start the one cycle training, we're going to set as a hyperparameter the smallest learning rate. And then a callback is triggered to find this optimally large learning rate. It uses Hessian-free optimization. So stochastic gradient descent is a first-order optimization method. This is a second-order optimization method. It represents the curvature in the error surface. So when you perform SGD and it's trying to find your global minimum, it's looking at the error surface as like a plane. But this is looking at the curvature. And it's quite expensive. So what you can do to compute it less expensively is to use conjugate gradients. And you're going to estimate the Hessian matrix to a vector. So what's neat about this is that the FastAI library does all this for you. You don't have to do it. And it's a very powerful way to find an optimal learning rate, an optimally large learning rate. So in one cycle training, we're setting these cycles to train through, right? We're going from a low learning rate to a high one and then slowly back down for most of the cycles. But in the initial cycle, in the very first cycle, we're going to find this optimally large learning rate, and we're going to train for the entirety of the first cycle at that optimally large learning rate. What that does for us is that it provides a regularization that speeds up training time for up to an order of magnitude. This is 10 times the training speed. And if you're worried about this, I would encourage you to go read Leslie Smith's paper from 2017, which I'll provide in the references for you. So again, we're going to train with one cycle using that large learning rate, and then we're going to train the rest of the time using slanted triangular cyclical learning. What's kind of funny is that we're going to get to the code in just a minute, and it's very, very simple. But that's because the FastAI library does a lot for you. Okay, so Howard et al., they trained this Wikitext 103 using training. And then we are going to use it to fine-tune the Wikitext 103 on the movie plot summaries from the multimodal IMDb dataset. Once we've fine-tuned our language model, we're going to basically use the weights from the language model to create a text classifier, which we will then again fine-tune using one cycle training. Okay, so let's get to it. Let's get to the actual code. But before you code, as always, every one of you know that you have to start with the data, right? So we're going to get data frame. Here you see the image path. We're not going to do much with that for now. Hopefully sometime in the future. You can see the tags. Now this is a space delimited set of tags. And then you're going to see the text. We start with the movie name and then the movie summary. Okay, what do you do after you create your data? You split it into train and validate. Now, I do not split into train, validate, and test because I'm not using my validation set to tune my hyperparameters. If I did, then I would have wanted to use a test set. But since we don't do that, it's okay. We basically use the validation set as a test set. We're going to use scikit-learn's train test split. And we're going to split the data into 75% train, 25% validate. All right, now let's import PyTorch. Hey, PyTorch, finally got to it. And we're going to import FastAI. So one of the first things that we want to do is we're going to want to set the device to use GPU. If you don't, this is going to take forever. It takes about 3 hours to do what we're about to walk through. You don't want to do it without a GPU. Now, we're going to use the FastAI library to load our train and validate set, and it's going to infer what kind of cost function we need from just the label delimiter. So it says, oh, you've got multiple labels. They're delimited by spaces. So you're going to use, it's going to be data for a multi-label classification problem. So you're going to need a loss function for that multi-label classification problem. That's kind of nice too. FastAI just bakes that in. So now we have this data bunch, and we're going to go ahead and load it into a language model learner with the AND-LSTM, which is our Wikitext 103. So we create a language model that way. Now this is what we just created. This is the language model architecture. What I want you to notice about this is that it has two parts. So the first part is an encoder, and it is our AND-LSTM. The second part is a decoder. So we're composing an encoder with a decoder. The decoder is a linear decoder. To make the text classifier from this language model, we're going to chop off the language decoder and replace it with a linear classifier, a pooling linear classifier, to be specific. So we'll see that in just a minute. All right, so now we have the model, we have the architecture, we have to train it. With the FastAI library, all you have to do is call fit1cycle on your language model. The parameters that you give fit1cycle are the number of epochs, in this case 1, that you want to train for, and your starting learning rate. Remember, we're going to give it the starting learning rate, and then it's going to find that optimally large learning rate to train the first cycle for. So this actually fine-tunes our Wikitext 103 with just the last layer. It's just fine-tuning the last layer. To do a little bit more fine-tuning, we have to unfreeze the rest of the layers and then call fit1cycle once again. So this time we're calling fit1cycle, we're going to train for 2 epochs, and we're going to set the beginning learning rate to 0.001. Okay, now we have a language model. Let's take a look at how it's predicting things. So we're going to call predict on our language model, and we're going to give it the beginning of a sentence, give it a little start. We're going to say, okay, predict 15 words. So it does, and it's okay. This movie really is a story that is Oscar Einstein's hit on the impending capital. And we believe it. Okay, so now we want to save that model because we're going to, again, use the parameters that we've trained in this language model to create our text classifier. Now, let's start creating the text classifier. Again, we're going to load our train and validate data. We're going to load our vocab from what we just learned. And we're going to make a multi-label data set for our text classifier. This time, it's going to give the text classifier tuples of text and tags to train from. The language model didn't need the tags, right? It kind of ignored the tags. It's just predicting the next word. Oh, okay. I think we're okay. I think we're going to be fine. So we load the multi-label data set, and then we load a text classifier learner. So that here you see we're giving the text classifier learner the data that we just loaded. We're giving it the AND-LSTM. That's the architecture. We're doing some dropout, and we're saying these are the metrics we want to use. We're going to use that F beta that I talked about before, and accuracy threshold, which we won't go into. Okay, and then on that same text classifier, we're going to load the encoder that we just saved. We're going to load that language model encoder. Okay, what does that look like? It looks like this. We have that same AND-LSTM here for our encoder, but now we have a pooling linear classifier for our decoder. Okay, we got to train it, right? So we're going to do the same one cycle style training. We're going to fit one cycle for one epoch using 0.01 as our starting learning rate. And then we're going to do something a little bit different. We're going to perform discriminative one cycle style fine tuning. So here we're going to freeze all the model up until the last 2 layers, and then we're going to perform one cycle training using a different starting rate for each of the layers. So on the second to last layer, we're going to start with 0.0025 as our learning rate, and on the last layer, we're going to start with 0.005 as our learning rate. So we fine tune that way. Then we're going to unfreeze all the layers, do one cycle training, with again this discriminative fine tuning, where we start out with a super low learning rate and we go to a slightly higher learning rate in the final layers. Oh, wow, I forgot the big ending. So we trained for 8 epochs and we get our final score. So you can see that our F beta is 0.734 or 73.4. Okay, so let's take a look at the prediction. Now we're back to that movie that we started with, What the Bleep Do We Know? Well, our text classifier is able to say, I think that's a documentary, and I think it's sci-fi, which I think is kind of okay. I mean, if you get into this red text, you can see that this movie is following Amanda and her neurological processes. Okay, so what's the conclusion? The unimodal text classifier in this research obtains an F beta of 73.4 during our final training epoch, and that reduces the error of Vallo et al.'s 2017 best gated multimodal unit by about 15%. So we have outperformed multimodal classification. And U2 can do this with the FastAI library.
I'm not sure I need that for sometimes if we develop and apply our methods to this basically traditional data sets for evaluation, I have the feeling that we run the risk of basically developing methods which are very well for this particular data set. So did you try your method on any other sets so that you can have basically a benchmark which is not related to this particular example?
That's a great question, and that's for my research to come. Yes?
In the earlier slides you mentioned images and text. You just focused on the text side of
Yes.
identification. How have you approached the images part and the different weights you've given in the earlier equations? I mean, how do you do that?
Right. So let me go back to, actually this is going to take a long time if I try to go back. I will just answer your question without the slides. So again, that is for future research. What I found was that I was able to outperform the multimodal classification of the unimodal text classifier, and it was pretty involved. So yeah, the next steps will be to train an image classifier and then to use a gated fusion to see if we see the same results that we saw with the other researchers, where we find that the text classifier and the image classifier provide kind of beneficial information to one another, right? So that the fuse can get a better score than either one of them together. Other questions? Yes?
I'm sorry I came a bit late, but I really got interested in the last argument that you made, that the two classifiers actually provide information that is mutually useful.
Yes.
So can you maybe give or try to explain why you think this gave us well? What is the similarity?
Wow.
Even if it's a guess, it's just it's intuition if you can see it.
Right. Well, I think, so this is definitely But I think if you look at how humans learn language, they don't just learn with language, right? So a mother and a father teaching their child what a dog is, they point to a dog and they say dog, so you have that visual information, right? And you're learning what dog means. So I think that it may sort of point to that here you have the visual information and the textual information, and they both provide distinct things that can help with classification, distinct attributes. Yeah.
So in a way they represent some sort of conceptual abstractions in two different ways.
Yeah.
More questions?
Okay, let's think.